sklearn, inspection, partial dependence display. A deep dive. The partial dependence display class in scikit-learn is a powerful tool for visualizing the relationship between a target variable and one or more features, while controlling for the influence of other features. This allows you to gain insights into the model's behavior and understand how different features contribute to the prediction. Key features. Partial dependence plots PDP. The main function of partial dependence display is to create PDPs. A PDP shows the marginal effect of a feature on the prediction, averaging over the values of other features. This helps understand how the model's prediction changes as the feature value varies. Individual conditional expectation ICE plots. Partial dependence display can also create ICE plots. Unlike PDPs, ICE plots show the prediction for each individual instance in the dataset. As the feature value changes, this can highlight heterogeneity in the model's predictions across different instances. Interactive visualization. Partial dependence display enables interactive exploration of the generated plots, allowing users to zoom in and out, focus on specific regions of the plot, select features, examine the effect of different features individually or in combination. Toggle between PDP and ICE plots. Compare the average effect of a feature with its effect on individual instances. Support for various estimators. Partial dependence display works with a wide range of scikit-learn estimators, including linear models, tree-based models like decision trees and random forests. Support vector machines, neural networks. How it works. 1. Feature selection. You specify the features you want to analyze. 2. Grid creation. The feature values are divided into a grid of points, covering the feature's range. 3. Prediction calculation. For each grid point, the model's predictions are calculated while holding the selected feature at the grid point's value and averaging over the values of other features. 4. Plot generation. The predicted values are plotted against the corresponding grid points, creating the PDP or ICE plots. Example: Python. Import matplotlib. pyplot as plt. From sklearn, datasets. Import load iris. From sklearn, ensemble. Import random forest classifier. From sklearn, inspection. Import partial dependence display. Load the iris dataset. Iris load iris. X iris. Data. Y iris. Target. Train a random forest classifier. RF random forest classifier. Random state 42. RF. Fitx. Y. Create a partial dependence display object. Display partial dependence display. From estimator. RF. X. Features 0, 1, 2. Kindboth. Show both PDP and ICE plots. Show the plots. PLT. Show key values in YAML. You provided a YAML structure, but it is incomplete. I will assume a general structure for partial dependence display configuration and explain the key values. YAML. General configuration. Features 0, 1, 2. Kindboth. Optional parameters. Method brute. N jobs -1. Grid resolution 100. Subsample 100. Random state 42. Customization. Line KW. Scatter KW. Grid range null. Contours true. Contour KV. Plotting. FIG KW. AX KW. Explanation of key values. Features a list of integers representing the indices of the features to analyze. Kind specifies the type of plot. Individual creates ICE plots. Average creates PDP plots. Both creates both PDP and ICE plots. Method. The method for calculating partial dependence. Options include Brute calculates predictions for every point in the grid. Fast uses a faster approximation method default. N jobs the number of jobs to run in parallel for faster calculation. -1 uses all available processes. Grid resolution the number of grid points to use for each feature. Subsample the number of samples to use for calculating partial dependence. Random state seed for the random number generator. Used for reproducibility. Line KW dictionary of keyword arguments to pass to matplotlib. PyPlot. Plot for customizing PDP lines. Scatter KW dictionary of keyword arguments to pass to matplotlib. PyPlot. Scatter for customizing eyes. Points. Grid range optional list of tuples defining the range of values for each feature. If none, the feature's range is automatically determined. Contours Boolean value indicating whether to show contours on PDP plots. Contour dictionary of keyword arguments to pass to matplotlib. PyPlot. Contour for customizing. Contour lines. FIGKW dictionary of keyword arguments to pass to matplotlib. PyPlot. Figure for customizing pay. Figure. AXKW dictionary of keyword arguments to pass to matplotlib. PyPlot. Axes for customizing the axes. Using partial dependence display for model interpretation. Partial dependence display is a versatile tool for gaining valuable insights into model behavior. It can be used to identify important features. Features with a strong effect on the prediction will have prominent PDP plots. Understand feature interactions. You can explore the joint effects of multiple features by creating PDPs for feature combinations. Detect nonlinear relationships. PDPs can reveal nonlinear relationships between features and predictions that might not be apparent from simple feature importance rankings. Evaluate model performance. PDPs can help assess the model's overall accuracy and identify areas where it might be performing poorly. Communicate insights. PDPs provide a visual representation of model behavior, making it easier to communicate complex information to stakeholders. Limitations. Computational cost. Calculating partial dependence can be computationally expensive, especially for large datasets and complex models. Overfitting care should be taken when interpreting PDPs, as they can be influenced by overfitting. High-dimensional data. Visualizing partial dependence becomes more challenging with a large number of features. Conclusion. Partial dependence display is an indispensable tool for model interpretation, helping data scientists understand how their models work and identify areas for improvement. By exploring the relationships between features and predictions, you can gain insights into the model's strengths, weaknesses, and potential biases, ultimately leading to better model performance and more informed decision making.